In this video, we are going to begin our discussion of differential equations. This beginning section is it's a bunch of definitions, just like the beginning of any math class. I will try to make these videos throughout the whole semester as short as possible, try to chunk them as much as I can so you can break them up as you need and you're not stuck watching a 50-minute lecture or an hour and a half, or I've seen 3.5 hour lectures before with a video. I'm gonna not do that to you. I'm gonna try to chunk them. So the beginning section here, like I said, it's a bunch of definitions. We have to define these things if we are going to talk about this topic at all. So let's start. Beginning with the class title, differential equation. This is an equation that contains derivatives. That's all it is. It just has derivatives in it. Now, these derivatives can be ordinary derivatives. That's what like Calc 1 and 2 dealt with, right? Or it could be partial derivatives, which is covered in Calc 3. Now, I know that Calc 3 is not a requirement for this class, so if you have not seen partial derivatives, now is the time to go study that. I would go look it up. It's not too bad of a topic. If you need help trying to find a video that talks about partial derivatives, I have a bunch of good ones I can send to you. So just reach out for help if you haven't seen a partial derivative. So with that, a differential equation is literally an equation with derivatives. That's it. It can be an ordinary derivative. It can be a partial derivative. That leads us to two different types of differential equations. We have an ordinary differential equation. What we call that is an ODE. And then a partial differential equation we call a PDE. We are going to be studying ODEs in this class. PDE is they have a different class. We're not going to touch it at all. We're going to see some, what they look like, but we're not going to study them at all. That's a whole different course. That's where a lot of the current studies are sitting. So now, why do we study differential equations? Why are you taking this course? The main reason is a lot of you guys are engineers, physicists, few mathematicians maybe. Most physics, laws, equations, formulas, and you guys have already been working in this, are differential equations. Now, some of them are pretty well hidden, and you're going to be like, oh yeah, you're right, that's a differential equation. But as you go up, you will see more of these things, and you're going to get used to them within your specific career. So let's start off with something that I hope you guys have seen before. It is Newton's second law of motion. So force equals mass times acceleration. Now, we can actually move this thing around to make it look like a differential equation. So let's recall that acceleration is the derivative of velocity. It is also the derivative of position. So U here is position, right? If I have a position function, I take the derivative, I get velocity. If I take the derivative of velocity, I get acceleration. Hopefully you guys know that at this point. If not, we need to talk. This third thing down here, where v is velocity and u is position. So all they're going to start doing now is they took this, we're going to take that equation, we replace this acceleration with the derivative of velocity, and then from here they just replaced the derivative of velocity with the second derivative of position. Over here is just telling us what variables there are, time and velocity. Here it just tells me that time is a variable, that position is a variable, and then we also have the derivative as a variable. That's all that is. It's just fancy writing for that. All you need to know is differential equations. They show up quite a bit. They're in our laws, they're in our formulas. We need to start working with them and figuring out techniques to solve these things. So here's some examples of DEs. Differential equations, we will start abbreviating them DE. So notice a few things. Let's make sure we're good with notation. If you don't recall, that is our second derivative of y with respect to, and they tell us what the variable is over here. It's t. This is our first derivative. This is the function itself. What we're actually trying to find, I do want to point this out, when we're solving a DE, which we're going to spend the whole semester doing different techniques just solving these things, we are trying to find a y. So we're trying to find a function. So y equals some mess with t in it, right? That when I take the first derivative and the second derivative and I plug it all into here, just like back when we were doing equations like this, we were trying to find that number that would work. That number is 5. When I plug that number in 5, I get a true equality. It works. It's the same thing here. I'm just trying to find a y, a function, that when I take the first derivative and second derivative and plug it in, that equation is going to work out. Now the problem is it'd be hard to check this because we don't know what g of t is, but that is a dE because it contains derivatives. All right, the second one, this is a second derivative, right? A first derivative, and then the y's are the functions, and then we don't have any x's, but that's still a differential equation. It contains derivatives. One thing here I want to remind you of, when we use this notation here, the prime notation, once we get above 3, we just put the number it is, the fourth derivative, in parentheses. We don't do 4 tick marks because it would get a bit. This is a typo. I apologize. I thought I removed all those, but I guess I didn't. That is still a dE there. Now, the next one should look a little different. Those of you that haven't had dE, you're probably like, that looks really intimidating. This is just the symbol we use for partial derivatives. We are not going to work with them, PDEs anyway, but we will be working with partial derivatives. So this is a PDE, while these were ODEs. They had normal derivatives in it, so it's an ordinary differential equation. This one had partial, so it's a partial derivative differential equation. This other thing, the partial, also we could wrote this as u with a subscript of x. That means the partial derivative with respect to x. If I add a second x in there, it's just the double partial derivative with respect to x both times. So both of these, all the remaining 3 here are partials. It gets a bit complicated here, but this is just the derivative of partial derivative of t, and then the partial derivative with x, and then the partial derivative with x. So like I said, if you haven't seen partials, you need to go look those up. If you need help finding videos on how to study those, what you should be looking at, please email or text me through the Google number that is in the syllabus or on Blackboard. All right, we are going to start adding to more definitions here. The important part, and I kind of want to talk about this pretty quickly, but in algebra, so let's say we had like this equation over here, 3x equals 15, and we got an answer as x equals 5, okay, right? We would start working up, if you were learning this for the first time, I would then be like, okay, we're going to do something like this then. And then you do 3x equals, and you add 3 and you get 15, and then you're back where you started. You have to be able to identify, though, that this is a linear equation. Just like if I got down to something like this, x, I don't know, minus 9 equals 0, I know this is a quadratic, and I have certain techniques that I use for a quadratic, as I have certain techniques that I use for my linear equations. If I had a square root function, right, we talk about those techniques, and they typically build on each other as they go up. DE is going to work the same way. We're going to learn techniques, and the thing is we need to be able to identify equations if I want to determine the technique I want to use, just like we did in algebra. Quadratic, oh, cool, that tells me I need a factor, or use my quadratic formula, or complete the square. Oh, a square root, I'm going to square both sides. I have techniques that I would use, but you have to be able to identify the function. Unfortunately, it's not going to be as straightforward as the algebra because we have a lot more going on. All right, so let's add to our definitions. I went ahead and defined this on the last page. A differential equation is an ordinary differential equation, abbreviated ODE. It has ordinary derivatives, and then the partial differential equations have partials in it. So if we go back, we have ODE, 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 and then the last 3 are PDEs. All right, you can check out those numbers if you'd like. I think that one's an easy thing to differentiate. You're just looking at the derivative. Is it a ordinary differential derivative, or is it a partial derivative? Okay, the next thing we're going to define is order. What order means is the largest derivative present, not the largest power, but the largest derivative. And you'll see why I differentiated power and derivative. So if we go back and look, let me erase some of this since I've written all over it. So let's go ahead and look at the order for this stuff. Forgot to erase. It's kind of weird with the... All right, so I'm looking at this first one here. All right, the highest derivative right here, is second. So it is order 2. All right, the next one, okay, I have a first derivative and I have a second derivative. So the highest derivative is a 2. So order 2 again. All right, this one, the highest derivative is a 4. So the order is 4. Here, the highest derivative is 2. I think you're getting the point, right? So the order here is 2. The order on this one, okay, this one's a little tricky. We have 2 partials there happening, XX, right? So the order is 2. And then the last one, I have a partial that's to the third. I'm taking 3 partials, so this order is 3. One thing I want to warn you about, and this is in the homework, when I have something like this is still first order. The reason is I'm not taking the 8th derivative. That's not what that says. That says take the first derivative and take it to the 8th power. It doesn't say take the 8th derivative. We wouldn't want to do that, right? Unless I guess we get down, it's linear and we get to 0 pretty quick. But be wary of that. That does not tell me 8th order. That tells me first order. But it's just the derivative to the 8th power. All right. Order's pretty straightforward. It is something that we are going to have to start noticing. In our 4th section, we start calling, we focus on first order, something called a linear equation for DEs. And we'll get to that in our 4th lesson. All right, so that's order. So let's get to that next definition that I was just mentioning. The next thing we're going to look at are what are called linear equations. This looks like quite a bit, especially when I give you the formula like line 11 there, this whole mess. But we just need to start looking at a few things. So I'm going to do some highlighting and try to break it down for you. Okay, so notice that is the nth derivative. Then I have the n minus 1 derivative. And then dot, dot, dot. Then we have the first derivative. And then we have the function itself. So notice those are my only y's. Right? Notice that it walks down the nth derivative, the n minus 1 derivative, and then these dots right here in the middle are walking down. So if it was the 5th derivative over here, it'd be the 5th derivative, 4th derivative, 3rd derivative, 2nd derivative, 1st derivative, and then here we need the function itself, so y. Now, here's a couple things. Those can be gone. Like I can have the 5th derivative, no 4th derivative, 3rd derivative, 2nd derivative, 1st derivative. But as long as I don't have anything weird with the derivatives, like the derivatives can't be to any power, they can't be dividing by the derivative, I can't take the square root of the derivative, I can't take the derivative and multiply it by another derivative, I can't take the derivative and times it by y, or anything like that, that would change it and it would no longer be linear. So the linear ones are walking down in derivatives. Now this other number here, this a sub n, and notice it says a sub n minus 1, and these are all, notice the t there, these are just functions of t, or x, whatever the variable, independent variable is. Y was our dependent. In this case, t is our independent. Those green highlights there can be anything with a t in it. It can be a 0. It could be a 5t. It could be a square root of t. It could be t to the 5th power. It could be ln of t or cosine t. It could be anything with t's or constants. Just can't have a y. And then the right-hand side is some kind of function of the same matter. So it like can only have t's, constants. It can't have a y. So the linear equations have 2 parts, even though it looks like a jumbled mess. We have the orange parts that are counting down in derivatives. And then the green parts can be anything with t or x, whatever the other variable is. All right, I would go ahead and get a read through that for your notes. I try to type up as much as I can to give you actual information. The book is going to be used as a reference. I would encourage you to go read it. There are going to be some methods that I don't care for in the book. The book is determined by the department as a whole, so we all kind of pick and choose what we like out of it. So I would go ahead and give that a read through with their definitions. It'll be a little bit different than this, same ideas though. All right, if it can't be put in this form here, 11, then it's non-linear. We only have, it's a dichotomy. It's either linear or non-linear. Okay. Let's give some practice for this. This is as far as it's going to go. We are going to classify by order, linearity, and type. What type means is ODE or PDE. So notice that the first one, let's take a look at that they are normal derivatives, ordinary derivatives. So I know it's an ODE. So I know I'm going to write OD at the end. The order is based on the highest derivative. Well, the highest derivative is the second derivative. So this is a second order. And then I know it's ODE. But now I got to determine, is it linear or nonlinear? Well, okay, let's highlight our derivatives. Second derivative, first derivative, function. Okay, so the y, or the dependent variable, is counting down in derivatives, and I have y's. Now all I have to do is check the front part and make sure that they don't have y's in it. That's really all it comes down to. Or another variable. We're good. The number's in front. The front number here is a 1. That's okay. I can have a 1. Then I got negative 2x. That doesn't have a y in it, just has x. So we're good. And then the number in front of the coefficient of y is 2, so we're good there. So this is linear. It matches that form. Okay, this next one, it is a PDE. So I know it's a partial PDE. Linearity doesn't apply in this context to the partial derivative. So you're just going to say the order, okay, it's second order PDE. You don't need to say linear or nonlinear for a PDE. All right, let's look at C. So let's do order first. Okay, this is that tricky thing I was talking about. dy dx is to the second power. That does not mean second order. This is a first order because it's a first derivative to the second power. A power is not the same thing as the derivative, even though that we typically put it in the superscript, it's different. All right, so it's a first order. Okay, since dy dx is being taken to a power, this is non-linear. Remember, for the linear equation, I need like the derivatives to count down and nothing to happen to them. Since it's just a dy dx, not partial, it is an ODE. Excuse my handwriting. I go back and forth the board and iPad, and yeah. Best we're going to get. All right, so D. So we're looking, this is a first order. All right, and then we got to determine linearity. Now, here's the deal. This big P right here is a constant. This K is a constant, but this P here is my my dependent variable. Remember, if we go back up to our definition, this is my dependent variable, the orange ones. I'm highlighting it, underlining in green there. The derivatives, nothing is happening to them. They're just straight up just the derivative. Can't be anything else but the derivative. It can be multiplied by something else, like some other function of t, but it can't be like the derivative can't be taken to a power. Can't be the square root, right? Here's some examples of like what y could not be taken to, or even the derivative, right? I can't have anything like that. So if I'm looking down here at at D here, there's another thing that we need to point out as well with that derivative, and I meant to go here. But if we look, we get a derivative counting down, and then also y here is not to the second power, it's to the first power. That's the linear part. They're all to the first power. Now, we have to make sure that whatever our dependent variable is, it's not taking to any other power except for 1, because we would lose the linear part. So if we're looking down here at D, this P has to multiply by that P, and it's going to give me a P squared, which means it's non-linear, because my dependent variable is to some power other than 1. This is an ODE because they are ordinary derivatives. All right, this last one here, or not last one, E, we have a second derivative, a first derivative, and a y. It walks down like that. The numbers in front are x's or constants, so we're good. This is a second order. Since the green there walks down, derivatives, this is linear. They're all to the first power. Nothing funny is happening to them. And then ODE since they are ordinary derivatives. This last one here is a bit tricky. The order is not bad. Fourth order, right? There's no other derivatives, so that's not too tricky. The linearity part is the tricky part. Now, notice that our dependent variable is y, so that's the part that has to count down. Now, this is what I was talking about where it's okay, because what actually is happening, and I'm going to use prime notation out of laziness, is we have this. And that was totally legal for linear equations. So this is linear. We can be missing terms as long as we're not multiplying by our dependent variable anywhere except for the derivatives and the function itself. We'll get the linearity part. So this is a fourth order linear ODE. All right, so I'm going to end this video here. It is extremely important that you can classify DEs, and we're going to add more to this, like different types of DEs as we go along. If you can't classify, you're going to have a hard time choosing a method to solve. Just like algebra, you had to be able to recognize it's a quadratic to solve it using quadratic methods. You have to be able to identify that it's a first order linear or second order linear and stuff like that. Okay.